That's not what I want to do. If we, just to kind of prove to like you guys, like, okay, like I think this is one part where I don't know. So Stephen, you might actually have more experience in the sense that because you've already in mod 4 right now, but actually making a gradient descent is that basically all it comes down to is that you have to know what equation you're starting, like what equation you're trying to maximize or really minimize, right? Trying to find that minimum point. And then once you know what that equation is, you can then say, all right, let me go ahead and find derivative of that first one. Once you have that derivative, then we can actually perform gradient descent. So the steps that we kind of do for gradient descent in general is we define the function, right? Then we say, what is the derivative of that function? And then we would say, okay, once we have that part for gradient descent, we need to say, all right, where do we start? So we're going to start with our gradient descent. So kind of going back to here, and this is the two-dimensional version, right? If we have some function, some funky function like this, we basically say, all right, that's our function f, which in this case is going to be our log likelihood, right, for logistic regression for MLE. And you say, okay, log, basically your descent, say, well, we start from somewhere. So let's say we start like right here. We have to start somewhere. And we say, all right, go ahead, calculate what f prime is around that point. And say, okay, move in that direction. And then you keep moving, essentially. And then the thing is you want to keep moving in that direction. But if you notice, if you go right here, well, okay, we skipped over it. So we're going to go back down. And we might kind of go back and forth a little bit. So essentially what we do is like, okay, we're going to take so many steps. Like at a certain point, we should just stop stepping. Because if we step forever, it's, when are we going to stop? So there's two things we can put in, basically say, all right, how many steps? So number, they call it like iterations. And then also saying, how precise do we get? If we get to a certain precision where we're basically stepping again back and forth, the same spot, we basically have found at that point. So like if you imagine if our precision is like, well, we only need it to be within this point, it's not really the best thing, but like let's say, I'm gonna write it with a different color, black. If I keep stepping back and forth right here, okay, if we're basically within this like little range, like, well, okay, we'll stop right now. We don't have to keep going because that's as precise as we really care about it. Because remember, computers can only be so precise, right? You'll never get the exact point with gradient descent. So we'll also put in a precision. So we have to say, where do we start? How many steps? And then, like I said, precision. Basically, when do we stop? That's what these parts are. Okay. So that's our steps for gradient descent. So it's actually not that bad to program gradient descent at this point. So basically, the first we have to do is just define what is our derivative. I'll just call it deriv. And we'll use it for x. We'll use it in one dimension. So our derivative of x, but it could also be like x, y, all that stuff. So I'm going to show you guys a general gradient descent of what that looks like. So let's say we start off with an equation like y equals x to the power of 4 plus, I figured this one before, that's why I'm writing this specific one down. Let's say this is the one that we're trying to maximize, but this could also be just our log likelihood, okay? But basically we need to figure this part out. It's like, all right, I wanna know what this function is right here. And I think I can go ahead and graph this. See, I already had it searched before. You can see on Google right here is that this is what the function actually looks like. So you can already tell the derivative, the minimum value, sorry, not the derivative, the minimum value will be about right here, okay? And so with that point, it's like, okay, cool, like this is the function we need to find. So what we usually will do, and we'll pre-calculate the derivative ahead of time. That ends up to be more computationally efficient versus trying to figure out the derivative and then use that. So in this case, what we'll have is like, all right, if we had the log likelihood, I'm kind of showing just an example, but the log likelihood, we already figured out the derivative. In this case, let's figure out the derivative here. It's like, well, that would be, in this case, 4 times x to the power of, what's it, 3? Plus 15 times, oops, times x to the power of 2. Oops. And then we add, oops, I don't know what's wrong with me today. 2 times x, right? So basically whatever this x is right here, we feed it in, and that will be our derivative, right, at that point. Okay, so once we have that point, it's like, okay, that's our derivative. So cool, we have our function. Again, this could be like the log likelihood. I'm basically not trying to do the lab for you guys right now, so that's why I'm giving you guys a different example. But essentially, this is your derivative for like whatever the log likelihood would be, or the derivative of the log likelihood, which the curriculum does give you. And then at this point, it's like, okay, cool. Then maybe we have to start at some place. Let's say we start at initial x is equal to, I'm gonna look at this graph ahead of time so it's not too bad. We're gonna start at 2, so it's not too high. So we don't go there forever. So initial x is 2. Okay, and then what do we need else? We need, when do we stop, right? So we need to say when is the precision. So we'll call it precision. And in this case, we'll call it just 0.0001. Basically, it needs to be within this range. So if we're basically finding, like, let's say the derivative is about like minus 3.01253, but then we keep going back and forth to like 0.53, 0.54, 0.53, 0.54, we can stop. That's what that precision is basically doing. Okay, and you can make this as big as you want. Just know that if your precision is too small, you might never reach it. If it's too big, obviously you'll stop before it's ever precise. If I put a precision of 1, then like if I skip over 1, like if I go from 4 to 5, then it's like, oh, well, we'll stop there because we're going to keep going back to 4 and 5. So just know that precision is basically how close to that actual minimum you want. And then let's see here. What else do we need? Oh, how many steps, right? So we'll call it steps, or we'll call it iterations, because that's usually what we call it normally. So we'll say we'll do at most, I don't know, 10,000, 100,000, why not, right? We have computing power. And so we have basically how many steps we have, where do we start? We're all good at this. We have our function derivative, right? So now we can actually perform gradient descent. And remember, with gradient descent, all you're basically doing is you're going basically back and forth, back and forth. So we started here, we calculate the derivative, we go down that derivative, okay? We can recalculate and put it through. One thing to do though, we need to notice is that sometimes the derivative is so big, we'll skip right over. So we want to basically scale down our step. And this is usually defined as alpha. So alpha basically is like, usually it's called our learning rate too. So just kind of know, I think that's might be a new terminology for if we just started Mod 3. But alpha is usually our learning rate. And so we'll call it, I don't know, usually it's like about 0.3 or 0.3 or 0.01. We'll start it with 0.01 since we're taking so many steps, okay? But this is kind of a little fudge factor to make sure that we have a smaller step so we don't overstep by accident. Okay, and usually it's about 0.01. It could be smaller, but if you make it too small, you make too small steps and you'll take forever to go anywhere. All right, so at this point, we can actually create our gradient descent. And so it's gonna be a while loop, basically. And so basically we keep doing this until what? Well, basically until we reach the number of steps or we finish our precision, right? So we need to basically say, okay, we need to put an initial part. So we can say our, what's it called? Basically, how big of a change have we made so far? Our step size, how big of a step did we do? So we'll call this previous step size. Okay. And we're just gonna find this as 1 because that's a pretty big step. Basically say how big of a step did we take, and that will be our decision. So while our previous step, oops, let me run this so I can actually do this. While our previous step is bigger than the precision, right? So while our previous step is bigger than this precision, we could keep going, basically, right? And then also we want to keep going while our the current iteration we're on is smaller. So basically, we haven't used up all our iterations. So let's have a counter. So I'll call it, and now we'll call it counter. Okay. Does that make sense? So we're going to keep, like, we're going to do 1 step, 2 steps, 3 steps, 4 steps, all the way until we get to, in this case, 100,000. Okay. So say while our counter, I need to run this. Our counter is less than the iterations. Okay. So basically, while this is true, keep going through it. right? So now it's like, okay, now it's the actual gradient descent part. It's like, all right, what's our, we say, okay, we want to make sure that we redefine every time we, what's it called? Like our x. So we'll take our x value, our first initial part, we'll plug into our derivative, we'll take a step, we'll calculate our derivative, we'll move down that by that amount, by a scaling factor, we'll have a new x, and then we're gonna take that new x, right, and then plug it into find the derivative again. So kind of looking ahead, we actually need something called a previous x, right? So our previous x is just going to be equal to our current x, but we don't really have one that's defined right now. So we'll call our current x is equal to our initial x. Okay. This way, we can make sure we always go forward into our, where we're going forward. Like we start from somewhere, we move over, and then we go into the next part. So using our current x now, all right, yeah, our current x, we can now say, okay, think of like what our new current x would be. So we take the current one that we had before, wherever we are in our slope or on our function. So we take our current x, and then we're going to, oops, I'm doing this wrong, sorry guys. We're taking our current x, we're taking the derivative at that point, right? So derivative of that current x. We're taking the negative of it because we're doing gradient descent, so we're going the opposite direction of the derivative. So I'll just do -1 just to make it more obvious. Okay, and then times our alpha, which is our learning rate, so we don't take as huge of a step. And then we need to add it from where we are currently. So we're right here, we calculate the derivative, we need to take it, basically this is our, if I make this more obvious, this would be our step size. So this is our step size right here, how big of a step we're taking. And then we can say, okay, what's our new current x? Where our new current x will be, that's right, yeah. Our new current x will be our current x, right? Plus, and I put, let me do that step size. We subtract off, no, I'm trying to figure out, that's right, we'll just put it like that, minus step size. Okay, just know it's because I'm doing the negative derivative. That's what's going on here. So this gives us our new current x, right? And then we want to basically increase our counter. That's equal 1, okay? And then for the heck of it, we'll print out where we are right now. So we'll print out f. Let's see here. We'll print out iteration number, this guy. Okay, so this will be our number of iterations, so counter. Okay, and then we'll also give what the current x value is. So x equals, and then we'll give our x value, which is our current x. And I'm realizing now, oh, I do, hold on a second, guys. I just realized I wanted to put something down. Previous steps, oh, this, we have to still test out for our previous step size, right? So we have to make sure that we calculate this part. So our previous step size, this is basically, we're done with our part. We have to make sure, hey, is our step size, how much of a change we did. And so we actually have, let's see here, because we're looking for the size, the absolute value of our current x, yes, minus our previous x. Right? Yes, okay. This basically says like, how big of a step have we done so far? Okay, so this will kind of give us like, okay, make sure we have this. And we're just subtracting this off to make sure we get this full part. If you notice this, you probably realize like, oh wait, I could have just done this part. But we're just making it more explicit, saying, okay, how big of a step did we do? So step from last time. Okay. And so remember we're finding this derivative here. So if I did everything right, we'll start with 10,000 just to kind of show you that. I don't know how long this will run. So good, it finished, which is always a good sign. So you can see here, we started with x in the 1.04, and we keep taking steps. And it turns out, if you look at it closer, we go negative, negative. So kind of going back to our graph, since we already made our graph, you can see here is that we started about here. And so we'll take some steps downwards, and we should end up about right here, right? So that's about minus 3.5. So for good, we should have reached about minus 3.5. Ah, we overstepped it. So you can see here is that we didn't quite work out. Is as we went further, smaller and smaller and smaller and smaller, we ended up not getting to that point. So I'm gonna make sure, you know, guys, I'm gonna copy what I had before because I know that worked last time. This is what happens with live coding, if I don't like live coding. And let's see here. And this is all the same basic stuff. I'm just kind of repeating it on here. And this time our derivative is this guy instead of df. So make sure we got this all done. That's 4. Why do I have this wrong? Well, there you go. You can see a gradient descent that doesn't work. So main idea here, but going through all those steps, I'd have to kind of go through and see like what exactly went wrong here in that sense. And I wonder if it's actually my derivative if I messed something up on there. So let's try a different derivative. Let's see if this will approach the right thing. So this is what I had before, is I'm just kind of changing it up. So this is a derivative of x squared, or this is the derivative of y equals x plus 5 squared. Okay. So I have this derivative, I have my previous step size. These should all be good now, and we'll see what that looks like. So, and now we have minus 5. So if I do this graph now of x plus 5 squared, you can see here I get minus 5 right here. So, and you can see, where was it? Okay. So you got pretty close. So I'm not quite sure. I might have messed up this derivative. I don't know. Or I'm trying to see what I might have messed up. I can't see it off right top of my head. Maybe you guys saw it at some point. Sorry, guys.
Maybe the order of operations.
Yeah, could that be it? Well, let's see. Let's see if I take a derivative, because I have a derivative here. Let's take a derivative of, let's say 0. Oops. 10. So right here, if we quickly look at that, going back. Okay, so at 0, it should be 0. And that is not what we have. So did I take the derivative wrong? Yeah, I think you're right. I think it might be something with the order of operations. So it might be something like this. Because that derivative looks right to you guys, right? Like nothing looks... Oh, I can do a derivative still. Okay, yeah, order of operations, you called it. So that's what happened here. So now if I do this guy, if I do this one, run the same thing, we'll get rid of this df. Now we should hopefully, what was the derivative? Minimum minus 3.5 about. So it should be pretty close. So now if I run this, cross your fingers, we get a very small number, close to 0. Interesting. Well, that was fun, guys.
Did you get to 3.5 earlier? And if you scroll up.
Oh, maybe it stepped over. No, I don't quite understand.
No, it just kept getting smaller and smaller.
Yeah. Oh, you know why? This is okay. This is a subtle point that I ran into last time. The reason why it's getting smaller and smaller is because right here it's feeling a local minimum. It's not going very far. So it's getting. This is actually a great learning experience. This right here basically is the gradient's getting so small that it's essentially 0. So 0 times whatever will always be a very small step right here. So it gets caught in this local minimum. We want it right here. So one solution you can do, and it's not something we talked about in Mod 3, but is important just in general is that you might want to start in different places. So instead of starting at 2, let's start at like -10. So you see a -10 is like all the way over here. So we should eventually go downward. So we'll see how well that works. Now, depending how big that step is, I might actually step over it, but let's see. I see, stepped over it. Result's too large. So let's start with something a little bit small. Let's start with -2. That should still be pretty small. There we go. There we go. Okay, and you can see here it's because I started with -2 right here.
Yeah.
So this is actually something important when you do gradient descent. You can see it's not perfect because it's only finding whatever is closest. And because this is this right here is such a flat area, basically what happens is like you can imagine like this momentum kind of going down and then you start slowing down and you never go further. So there's a couple of solutions you can do with this to avoid these kind of problems is you essentially randomize where you start off at. So you say, oh, let me start here, 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 like we saw with a different position. Another thing we can do is something called momentum, which I don't think we talk about right now, but you can use momentum, basically say, all right, remember how fast you were traveling beforehand and use that to kind of push yourself over these weird humps and like basically make sure that you find that global minimum. So there's a few strategies to go through that, but strangely enough, this function tends to be too flat at x = 0. But if you don't run into those parts, it still has. So limitations of gradient descent, but you can see it still overall does work. It's good. Good. I started getting concerned about what I was doing. I was like, do I even know how to do data science? So, all right. Any questions, you guys? But anyway, the reason why I show this is that you basically just need, essentially, everything's exactly the same, except figuring out this derivative. And that derivative for logistic regression is going to be the log likelihood. Which does show in the curriculum. And it's, unfortunately, I didn't write it right. But for a binomial distribution, it's relatively simple. It's just essentially counting the number of times it happens.
I have a question. This equation that you used, is this what a logistic regression would look like, the way it's graphed?
You're talking about this one? Or
the one that's commented out at the top? Yeah.
Oh no, that was just a random equation.
Okay, so just a toy equation.
Yeah, exactly. And this could have been multidimensional too. This could have been x and y. So I could have had something like, you know, y is this one, for example. Like that could have been the original equation. And I could call this like just f. And I could say, okay, like what's the derivative of this thing? The partial derivative, the gradient, essentially. And that would be like a derivative of x in y. And so the idea here is that you have the derivative. And once you have the derivative, the formed function, you can basically use that to proceed forward. And that's why we do that, that log likelihood, is because log likelihood is a lot easier to deal with than it is with the regular likelihood, and then taking derivative of that just turns out to be more work.
When you're referring to log likelihood, you're referring to the maximum likelihood, right?
Yeah. Yeah. Okay. Well,
the log version of the maximum likelihood.
That's right. Okay. And that's the thing. It's not that we're finding the equation of the maximum log, like that equation I wrote is not the maximum log likelihood. It's just the log of the likelihood. And we're trying to find the maximum via gradient descent.
So the equation is like all of the likelihoods.
Yeah, exactly. It's like
reverse it to find the best one.
Essentially what we're doing, I don't think I actually ended up saying this, but if we had a bunch of, oh, I just realized what time it is. But if we had a bunch of like logistic regression lines like this, you would say, oh, this logistic regression line, and then we'll try a different logistic regression line. It's a little subtle. Basically what happens, I realize I'm running out of time, but if I went from here, I could remap it to essentially a linear regression where our points that are at 0 or at 1 end up being at negative infinity or positive infinity. And I can create my line here and then map them over and then say, okay, what's this value supposed to be? And then reconvert it into a probability, which again, basically just comes down to saying we're making different logistic regression lines and saying which one maximizes the likelihood of this logistic regression. So yeah, so that's why we do the log likelihood, is basically saying if we keep changing our logistic regression curve, what that will give us our different likelihoods, and then say what's the maximum of those likelihoods, and that's what the gradient descent will find. Okay. Hopefully this didn't confuse you more. All right. Yeah, so that kind of finishes up. You guys have any last questions before I go and stop it up?
Yeah, thank you very much. I appreciate it.
No problem. Hopefully it's been helpful in some ways. But all right, I'll go ahead and stop recording then.